Heat is everywhere, and it is becoming increasingly important to find new ways to power our society. Luckily, there is a source of energy just waiting to be tapped into: heat. Heat is produced in almost every process that involves energy, especially in energy production and industrial processes. When industries produce products or energy from other sources is produced, they produce with them large amounts of energy that is usually dissipated into the environment. This dissipated heat may be up to 60% of the total energy used in the United States annually. So what if we could harness that 60%? Researchers are currently developing new ways to capture this heat energy and use it so that not as much goes to waste and makes industrial production much more efficient. In addition, methods for capturing heat energy within the Earth are also making strides in the energy sector and could potentially be the primary energy source for modern day societies. The universe is always increasing in entropy, moving towards a more chaotic state. Therefore, it follows that a lot of heat energy would be produced and then dissipated into the environment in industrial processes. Our job as humans is to reduce that as much as possible until it is no longer feasible to do so that we don't have to get as much energy from other sources like fossil fuels. The entropy changes of a system can be described by the equation S equals Q divided by T, where Q is heat entering the system and T is the temperature of the system. So, as more heat is produced, the entropy of the system will increase. We can also think of it in terms of solids, liquids, and gases. When something is solid, the particles have less energy and are much more orderly. When it's a liquid, the particles have more energy and are less orderly, or have a higher degree of entropy. And this is much the same as in a gas, in which the particles have more energy than a liquid and are less orderly than in a liquid. We can limit this heat loss in a number of ways. We can use batteries to capture escaping energy, or we can use materials that conduct heat in such a way that they induce an electric current, which gives us a way to transfer the heat energy into something useful, electricity. Or we can use heat energy from natural sources to heat buildings or power turbines that in turn create electricity. Batteries are nearly ubiquitous in modern society, and we probably wouldn't be able to have many of our modern conveniences without them. Batteries are now being used to harness the waste heat generated from industrial processes. This process is based on what is known as the thermogalvanic effect, which is the idea that the temperature of a rechargeable battery has an effect on its voltage. To begin, a rechargeable battery is heated with waste heat produced by some other process, then has a voltage applied to it. The battery is then allowed to cool, and the thermogalvanic effect causes the voltage to increase as the temperature decreases, resulting in more electricity being present at the end of the process than was used to charge the battery in the first place. It's important to note that the energy of the battery does not increase. It's the amount of electricity present in the battery that we can use and harness that increases. This system is unique in that it can operate at very low temperature gradients, some as low as 50 degrees Celsius, and at heats of less than 100 degrees Celsius. In the experiments, which were done at 60 degrees Celsius, the electricity conversion efficiency was 5.7%, which is double the efficiency of other more conventional thermoelectric devices. Interestingly, this concept was experimented with and used in the 1950s, but mainly at temperatures of 500 degrees Celsius or greater. These temperatures are generally not seen in conventional industrial production and energy production systems, so that's why it is important to develop technologies that can work efficiently at lower temperatures. Luckily, this process takes advantage of taking existing technology and using it to do something new, which makes it an extremely cost-effective and appealing option. While rechargeable batteries propose an interesting and probable solution to the problem of heat waste, another interesting and potentially useful concept is thermoelectric materials. Thermoelectric materials allow heat energy to be converted into electricity, but have thus far been too inefficient to use. They work by using heat gradients to allow for the transfer of electrons in the material, thus generating an electric current. In addition, they are rare and usually most effective at higher temperatures. So more research is needed in order to make this more cost effective and efficient at lower temperatures. One of the methods for harnessing heat produced from the environment involves a different natural source of heat, the sun. The sun produces far more energy than we need to power our society, but figuring out how to harness all that energy has been a scientific challenge throughout human history. The primary method for harnessing solar energy is by using what are called photovoltaic cells. These cells are made of materials that generate electricity when exposed to light and create a lot of heat waste in the process, making their efficiency extremely low. As we discussed earlier, thermoelectric materials can be used to convert heat into electricity. So, researchers have experimented by coating solar cells in thermoelectric materials such as cesium. As solar cells convert light energy into electricity and heat waste, the coating in turn converts some of the heat waste into electricity, improving the efficiency of photovoltaic cells and making sure that less heat escapes into the environment. This is especially true at higher temperatures, at which photovoltaic cells are notoriously inefficient. In addition, the addition of the coating can in effect cool the cells down, improving their efficiency in more ways than one. Another form of energy capture utilizes the heat found within the Earth, produced mainly in the mantle as radioactive materials decay. The most important part of this heat energy is that it is constant and abundant. Today, geothermal energy is largely untapped, with an estimated 38,000 megawatts of energy capable of producing 308 million megawatt hours of electricity annually across 13 states. So, if there's this vast reserve of energy just below our feet, how do we capture it? Most geothermal plants use what is called hydrothermal convection, in which cool water from Earth's surface seeps into the ground and is heated up, causing it to rise to the surface, usually in the form of steam. 3 different methods of hydrothermal convection exist, and can be used depending on if the water rises as steam or just hot water. There's a dry steam power plant, in which steam from the Earth turns a turbine. And there's also a flash steam power plant, in which hot water is turned into steam by applying heat to it, which then turns a turbine. Finally, there's a binary cycle power plant, in which hot water rising from the Earth causes a liquid that has a lower boiling point than water to vaporize and then turn a turbine. This method has much more potential than the other two in terms of growth. The specific processes are slightly different, but the end product is the same. The resultant steam is captured and ultimately used to drive a turbine, which produces electricity. The steam or hot water is then injected back underground in order to keep the cycle perpetuating. If this didn't happen, the water would eventually be all be used up, and a geothermal power plant would not be able to generate electricity from that hydrothermal convection cycle anymore. This type of energy conversion is extremely effective, with the plant in Northern California producing over 60% of the electricity for that region in a given year. Another form of geothermal energy that is projected to be able to provide over 4 million megawatts per year, known as enhanced geothermal systems, utilizes heat energy deep within the Earth that is available on a much larger scale than heat wells currently being used for geothermal energy production. These 4 million megawatts per year would be able to provide the power to power the entirety of the United States for an entire year. By tapping into heat energy in dry rock formations approximately 4 to 10 kilometers underground, it could heat millions of homes. Finally, Geothermal energy can be used to directly heat and cool buildings by taking advantage of the constant temperatures present underground. This is usually done through heat pumps or pumping heat from direct sources like hot springs for hot water or other things like that. For the most part, these systems are far more efficient than electric heating and cooling, and much more environmentally friendly because they don't involve the burning of greenhouse gases, which emit carbon dioxide into the atmosphere. So, moving forward, geothermal energy seems like it would be one of the most efficient ways to use heat found naturally and could potentially replace the other avenues from which we get energy with an abundant renewable source of heat energy.